manifold. First few remarks about the definition. I mean, the fact that this uses a topology and so on. Actually, it's a good idea to make first a non-trivial example. Especially by non-trivial, I mean something, again, which does not come from a subset of something, okay? Because otherwise, everything becomes a bit. So, in fact, for example, let's construct the real projective space. This is a game you can do actually also with other fields. So this is PNR or RPN. I mean, you will find it written in many ways. Okay, but that's always the same thing. So, okay, as a set, I hope you know what it is. Geometrically, it's the set of lines through the origin in Rn. Okay, let's be a bit more algebraic. So, as a set, PNR is by definition Rn plus 1 minus the origin, quotient an equivalence relationship, minus the origin because otherwise the equivalence relationship I'm going to write is not an equivalence relationship, where I say the 2 points xn plus 1 is equivalent to y1 yn plus 1 if and only if there exists lambda, a non-zero number, no? If they are one multiple of the other. So okay. So geometrically, two vectors must be proportional. Also reversing, I mean, lambda could be negative, so you can go in both, you can reverse the orientation of the vector if you want, okay? So the equivalence classes are denoted by what we call x1, xn plus 1. Okay, so these numbers here are called usually the homogeneous coordinates of the point. Okay. Now, the point is not all can be zero. There could be some zeros here, but not everything because I removed the origin from this game. So when I pick a point in the real projective plane space, at least one coordinate is non-zero. One homogeneous coordinate is different from zero. Okay. So, and then if it's non-zero, I can divide by it. And so everything. So if let's say xi is different from 0 for some choice of I, then of course x1 xn plus 1 becomes equal to x1 xi minus 1 1 xi plus 1 xn plus 1. Okay, so there is always a representative with 1, exactly 1 in the coordinate, which is different.
You should write that by all the other.
Sorry, yes. Otherwise, it's equivalent to something of this form. Okay? Yeah, I can divide by 0. So this gives me an idea of how to construct charts, because of course it means the set of points which has, for example, this coordinate, this homogeneous coordinate. These are not coordinates in our sense. Huh? These are homogeneous coordinates. It's another thing. If the ith homogeneous coordinate is non-zero, basically means it's useless. It's not telling me anything interesting. So I should drop it in some sense. And in fact, that's what I want to do when I construct our charts as differentiable manifolds. So define. In fact, has the course in algebraic geometry already started? Yeah, so I'm sure you have done this. So the affine coordinates, in some sense, I'm constructing. Okay, so the affine chart would be VI to be simply the set of points Okay, so this runs, how many of them I have? I have as many as real coordinates on Rn plus 1, so I have something like this. Okay, so on VI, we define the coordinate functions yi to be simply, on VI we define yj, okay, to be xj divided by xi, okay. So where now j goes from 1 to n plus 1, but it's different from I, because of course in the ith place I would get just the constant function 1, and I drop it, I forget it, okay? So remember, in order to construct a differentiable structure, what do we have to do? We have to construct x alpha from u alpha to the set M. So of course here alpha is naturally I, okay? So in fact I have a finite number of them, xi. The open set, which is parameterizing these objects here, is the whole of Rn, because once I kill the useless coordinate, I'm left with all possible numbers, okay? So I take Rn as domain of my chart, and I go to P and R, but actually I know already that I'm going to hit only Vi. Okay. Doing what? Well, now I reconstruct, I take y1, yn, and I just go into Vi by taking y1, yi minus 1, 1, no, these are sometimes commas, sometimes double dots, it's really up to you to decide how to indicate this, yi plus 1, yn. Okay? Set theoretically, there is no problem in the sense in showing, I mean, of course, it's immediate. Just to look at it, that this map is surjective. Okay. Now the question if this satisfies the change of charts properties. Okay, so we need to take two of these things which overlap and see which is the transition function from one to the other. Okay, so, of course, I mean, the other obvious thing to check is that the union of all this, they form an atlas, because of course, any point in Pn lies in some of these, okay, because of the observation I did before. Okay. So, so now pick two of these things, Vi and Vj. Okay. For any choice of I and j, they intersect. So I don't have to say, in such a way, in the general definition, I should have taken alpha and beta such that x alpha of u alpha intersect x beta of u beta. No? Here, I know that for any choice of I and j, Vi intersects with j. Okay, there is certainly a point which has both the ith and jth coordinates different from 0. Okay, for sure. I mean, I put one and one. If it has two ones in these two places, it lies in this intersection. Okay. 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 How do we want to construct the change of chart? I think it's better to decide, just to avoid confusion. Suppose what? That I is greater than j. Okay, let's decide which is the smallest of the two. So what is xj what we have to construct is xj inverse composed xi. Okay? Acting on what? Acting on the subset of Rn. I mean, each of these is defined on Rn, but remember the picture, I don't want to draw it once more time. I mean, this only on the inverse image of the intersection of the charts. Okay? So I'm not going to really to say, of course, what is the, if I take xi in this language, okay, so it's xj inverse, okay, xj inverse will come back here on the ith domain on these points where the jth coordinate is 1. Okay? I'm not even going to write it. So this is equal to what? This takes a point, y1, yn, and gives me what? Okay, this gives me xj inverse of xi. Xi puts a 1 in the ith place. And now that I have a 1 here, I have to do the opposite of this procedure, but now on the jth coordinate. So now I'm assuming that j is here, j is bigger than I, so it's one of these coordinates. And that means I have to divide by yj on this thing. Okay? So, well, okay, so this is xj inverse of y1 with the square brackets, yi minus 1, 1, yi plus 1, yn. Okay, this is by definition. And now I know that this actually is dividing by yj. So this becomes y1, and now with the round brackets, then there will be, okay, this is the first and last time I'm going to write all this stuff. Yj minus 1 divided by yj, 1, yj plus 1. Of course, if this makes sense, because otherwise j could be n, so then there is nothing like j n plus 1, or, well, actually n plus 1 exists. No, because here it stops at n. So j, y, n divided by yj. Okay? Okay. Now, the question that the definition of the differentiable manifold asks is this function differentiable? Well, the answer is no, in general, but yes on the right domain. Okay. Yeah, I'm dividing by something. I mean, this something, I avoided saying where this was defined, but where is it defined? It's defined precisely on the inverse image of the gray area in the picture. And that's precisely yj different from 0. Okay? So we are fine. So this is C infinity on the set yj different from 0, which is exactly what we want. Okay? Which was precisely the domain where we were looking. So it's fine. This gives a differentiable structure. Note, this differentiable structure, as we said, so every time a differentiable structure induces a topology. I didn't spend one word about the topology of the space because I know that the general theory is telling me if you define a differentiable structure, you get a topology for free. On the other hand, this is a prototype exercise in topology. Okay, you could have, without knowing what is a differentiable structure, you can say, well, this object has a natural topology by itself, by its own means. Okay? In fact, it's it's the nicest example of the quotient topology. Okay, it's you take the quotient topology of the Euclidean topology here. Okay? So now it's obvious to check that the topology induced by this differentiable structure is actually the same as the natural topology as a quotient. Okay? You can convince yourself in a second, because what is the topology induced by the differentiable structure is what? Is the one which makes these maps open. Okay? Which is actually another way, an equivalent way, if you look at the maps, to say what is the quotient topology. Okay? I assume you are all familiar with the projective space, okay? Check. Very well. Okay. So these are, when you do a little bit, when you go in the direction of algebraic geometry, these are called affine coordinates, and these are the homogeneous coordinates, okay? In differentiable theory, we will just speak about homogeneous coordinates are nothing in terms of general differentiable manifolds. It's just an accident of this very special situation. So the word coordinate should not interfere with your, okay? That's it. We will come back to this example, because this is a prototype example of many phenomena. You see, in fact, what is it's of dimension n, okay? So you start from Rn plus 1, so this is, for example, if you take n equal to 2, in fact, a standard obvious problem is to decide what is the relationship between this space and the sphere. It seems to have a lot to do with the sphere, okay? Seems kind of a strange cousin of the sphere, okay? Have you seen it, for example, in algebraic topology, this? We'll come back probably today about that. Let's see. Okay, so this is just one non-trivial example of a differentiable manifold, which, by the way, I could have not really, this has nothing to do with the surfaces in R3, even in the case of a surface. I mean, there is one situation that you can really say it's a surface, no? N equal to 2. You would think, you would call it a surface because it's two-dimensional. So the obvious question is, does this have anything? Is it a regular surface in R3? Okay, this is the abstract description. But can I realize it as a surface in R3? And actually, that's the answer is no. Okay, this is probably the first thing, the first object you see that has actually nothing to do. Well, also the hyperbolic plane, if you want. In that case, the problem was the metric. In the case of the hyperbolic plane is a disk. So, of course, it's everything you want in R3. Okay? But the metric you put, the first fundamental form is the obstruction. Here it's actually the topology. Okay? The topology, it cannot come from the topology of R3. Okay, now we have the definition of differentiable manifold. So, as I said at the end of the last lecture, we have automatically the definition of a differentiable function, and in fact, let's write directly, if you remember, now you can go back to when we studied surfaces. I first defined what is a differentiable function with domain on a surface and target real values. Then with the domain Rn and target a surface, and then between a surface and the surface. Okay, now we can do everything in one shot. You have grown up in this month. So now if I take two differentiable manifolds, and in fact, let me denote the dimension as a kind of a upper index, okay? So I have M1 of dimension n and M2 of dimension m, differentiable manifolds. Now, a map phi from M1 to M2 is differentiable, so now I'm defining what it means to be differentiable between two manifolds, if there exist charts, so let me call them y and u x, right, with lower, okay, for, so let's see, vy I want it to be for m2, so for m2 and m1 respectively, in such a way that phi of x of u is contained in y of v. So first of all, the image of the chart of the first one goes into the chart of the second. This I can always achieve by taking smaller and smaller domains, okay? So this is just by continuity of the thing. So contained in y of v, and now the real condition is that y inverse composed phi composed x. So where does this map goes? So this goes from u, which is a subdomain of u, is a chart for m1. So u is a subdomain of Rn. Okay. And goes where? Well, you go to m, to m1, then to m2, and now you force it to go back to Rm, okay? So to V, but okay, to V inside Rm, and so we are back exactly as we did for surfaces. Here the only difference is that here we have 2 and 2, okay? So if this is smooth, okay? Okay, a little mistake in my definition. Yes, if there exist charts, but this has to be around any point. Okay, so this would be, it's a smooth map around all points contained in x of u. So being differentiable is a local property, you know? So for every point hit by x, this is the definition. But now if I'm speaking about globally, a function, when is a function globally differentiable, this has to happen for any chart, I mean, around every point of the domain, okay? So if this is smooth, and this holds around any point, so now you understand what I mean. I explained to you in words what it means. It happens around any point. Okay? So for every point of the domain, I can find a chart on the domain containing this point, such that there is another chart on the target, okay? Any point in the domain. Okay. Then, as usual, in fact, in this situation, in the abstract situation, it's easier than in the classical situation of surfaces. If it happens for some charts, it happens for every chart. Because the change of chart property, the change of chart has to be smooth, okay? For any possible change of chart, okay? So in fact, this looks like checking that if a function, the smoothness of a function seems to be a mysterious thing, because you say, I have to prove that there exists two charts that maybe are very special, and then you immediately realize that actually if it happens for one choice, it happens for every choice. Okay? So in fact, it's very easy. So you can pick your favorite chart of anything and you check if the function is differentiable or not. Okay. Okay, so this is all basic material, but now let's move to the more delicate thing. The more delicate thing, as I anticipated to you a few times about manifolds, is actually the construction of the tangent space, because that's really the moment where we feel we really miss the ambient space. Everything was incredibly simple if we had somewhere something around our set. Now, the actual definition is not is not difficult anyway. It's actually, to me, it's really more psychological, because what it means. And we are used to think of tangent vectors as real vectors, real objects, I mean points in some space, okay? And that's the thing you have to stop thinking about. So, in fact, the winning idea goes actually back. I have to talk 3 seconds just to wait for the blackboard to dry. So, is to stop thinking of a tangent vector really as a point in Rn, as a vector in Rn, but actually as a functional in some sense. But this is something you know already from calculus. You can identify a vector actually with the action. I mean, if you think of a direction, okay, the direction you can actually represent it with a point, with a vector, in our sense, with a choice of coordinates. But actually you can also think of a direction as something which acts on functions, taking the derivative in that direction. I mean, this seems an overcomplicated thing to do. You say, oh, come on, the direction is a direction. I give you the point 1, 0, 0 is 1, 0, 0. So now, instead of thinking of 1, 0, 0 in R3, for example, I really want to think of 1, 0, 0 as the object which takes the derivative in the x direction. If x, y, z, no, 1, 0, 0 is the x coordinate. Okay, I'm thinking of this as the vector, as the thing which takes a function and gives me the partial derivative with respect to x. Okay? This is the winning idea. Okay? Let's formalize it a little bit. So, in fact, suppose for a moment we really are, what do I mean? I mean, let me first formalize it still in Rn. So, if I take a curve in Rn, let's go back to a moment of what it really means to take the tangent vector to a curve in Rn. Okay? So, and I mean, here as usual, I give a name to the initial point. So, what we used many times was the following, is that, of course, we take the bunch of functions, which gives me this, if we are in Rn, I can certainly do that. And actually, up to here, I can imagine how it will go, because on any manifold, I can think of a curve by taking its representation in a chart. So up to here, I'm not too worried. And then, when I said this is this, okay, now I want to reinterpret this formula just by saying if f is a smooth function around, of course everything is local, so what I really mean is really just around P, I can look at f restricted to alpha, which basically means f composed alpha. Okay? In fact, let's give this object a name just to, okay? And then, I really look at and the directional derivative of f in the v direction. Okay. Now, since we are in Rn, I know what to do. In fact, this is equal to what? Is actually f composed alpha prime at 0. Is the derivative at time 0 of the function restricted to the curve. This is by definition the directional derivative in the direction of v, okay, at the point P. But remember, we did it many times, but let's do it for the last time. So this is what? By chain rule, no? F is a function of x1, xn. These are functions of t. So if I express this thing in terms of what do I get? I get the sum of df dxi at t equal to 0 times x prime 0. Okay? Just chain rule. Okay. I want to see this object here as the output of an operator acting on the function f. So I want to put this f outside. Seems I can do it. Of course, this is just a picture. So these are numbers, no? This x prime at 0, these are numbers which multiply this operator and all this acts on the function f. Okay? Okay, so now you see where I'm going. Because by this simple manipulation I constructed something that actually now makes sense on any differentiable manifold. Okay? Let's think a moment why. So in fact, let me first give you the formal definition. This was in Rn because I still use these things here. I'm getting them from Rn, from the Rn representation of my curve. But this gives me the idea. So M is a smooth manifold, and alpha now is a curve in M. Of course, I'm assuming this is smooth in the previous sense, okay? Because the interval is a manifold, the manifold is a manifold, and so now I know what it means to be smooth between manifolds, okay? Of course, alpha of 0 is equal to p, just to give names to things. And now I will call curve D the set of functions defined around P and locally smooth. The point is that I don't want to be even more precise because I really don't care how big is the domain of definition. It's enough for me that the objects here are defined on an open set which contains the point P. I don't care how small it is. As long as there is a little ball, I'm fine. Okay? And they are smooth on this ball. Okay? So the tangent vector to alpha at t equal to 0 is, well, I still denote it as alpha prime. You see, the point is that I'm making sense of this symbol. Now this symbol has no sense. I don't know what it means. So this is the definition. Is a function from D to R. Okay. Given by what? I take a function f and I give you this. Okay? I give you the directional derivative in that direction. Okay? Actually, so everything is tautological when you say it in words because I'm defining the direction. Okay? So So the tangent space to M at P is of course just the set of all possible tangent vectors to curves. Passing through. Okay. And of course, we give it a name. Okay. Now, okay, formally this is okay, but what are we really doing? Let's go back, let's use charts, okay, to see what is the local representation of a tangent vector. Okay, in a chart, if in a chart means now I suppose that alpha, the image of alpha is contained in some chart xu. Ux. Well, actually, this is again is exactly the same computation we did for surfaces. So I need to give a name. So I have P on M. Okay, if you remember, I mean, always this picture. So I'm looking here. This is the area, the part of the manifold covered by the chart, and this is the domain. This is X. So if this is P, there is another point which is important here, which is the point corresponding to P inside the domain, which is called, I will call it Q. So, and if anytime I pick a curve here, alpha, there is a corresponding curve here composing by X inverse. Okay, we were used to call it beta. No, we don't need it. So the point is that X inverse composed alpha of T will be a bunch of functions. So we are back in that situation, in the starting situation. And so now, if I'm asking what is alpha prime of 0 acting on the function f, okay, well, this is that, but the only thing I have is the definition. This is d dt equal to 0 of f composed alpha. But now, I played this game, so I know already what it is. I mean, I don't repeat this computation. But now symbols have a different meaning. In fact, in some sense, I'm giving meaning to this symbol here. So of course, this becomes sum from I to equal to n of x prime I 0 d in the xi 0. Let me call it just like this. F. Okay, that's just the same computation. So this is the local representation of a tangent vector, because now that means what? So now from this I get a formula, whatever that means, that alpha prime 0, I mean, this function acting on f is equal to this object acting on f. So, okay, this is telling me that this is the sum over I of x prime I 0 d dxi. Okay, these two objects act on the same way on any function, so they are the same. Okay. So now, the whole point is really convincing yourself that there is something going on here. For example, what does it mean, this formula? If I take the coordinate curve, I take the coordinate curve t, 0, 0, 0, 0, the first one. Okay. So here, of course, what do I really get is that I get x1 prime equal to 1, and then everything is 0. Okay. So what I'm really saying is that ddx1 is a tangent vector to the manifold, which is actually the tangent vector which acts on functions by taking the derivative with respect to dx1. You understand? So this object here now, at least every time I have a chart, I have a bunch of tangent vectors for free, but the only problem, you have to digest the fact that now the tangent vector is this one. This is a tangent vector. because actually it's the tangent vector to the coordinate curve x1, comma 0, 0, 0. Okay? So the choice of a chart gives me automatically n tangent vectors, which are ddx1 up to ddxn. Okay? The partial derivatives in the coordinate directions. Okay? Now, another subtlety, but now everything is important. I can use this representation to, up to now, the tangent space to the manifold is just a set. It's a set of functions acting, is a set of derivation, no? Acting on functions. So, I want to give more structure to that. So for sure, I want TPM to be a vector space. I want to be able to add the vectors and so on, or to multiply a vector by 3. Note that this definition is very unfriendly in this respect. So suppose you take two tangent vectors, alpha prime of 0 and beta prime of 0. How do you add them? Well, of course, you can take this plus the derivative of f composed beta, but this doesn't prove that this is a tangent vector. Remember, it's always, actually we faced the same problem when we studied surfaces, but that, again, that was easier. I mean, you understand that if I formally write d of f composed alpha in the t plus d of f composed beta in the t, I wrote something, but what you really have to prove is that this is d of f composed gamma. I mean, because the set, to prove that this is a tangent vector, it has to be the derivation with respect to some direction, so with respect to some curve. So how do I build gamma out of alpha and beta?
We go to chart.
Exactly. I go here. Okay? So, but if I go here, all the problems are solved. In fact, even multiplying by 3 is a problem. I mean, what does it mean to take 3 times alpha prime of 0? Well, okay, I can put a 3 here, but I mean, for sure, it makes sense to, but then I have to prove that there exists an alpha. Well, okay, in that case you can manipulate, but okay. In any case, all the problems are solved here, but then I gain another problem. Why are solved here? Because if I give you alpha prime is something like this. Beta prime will be, call them yi, the coefficients of these vectors. Then, of course, what I really do, I take the vector space structure generated by the ddxi and I use it. So I declare this plus the sum over I of yi prime 0. So if I have another curve and another tangent vector, now I know that everything will be written in this form. Okay, so what it means to take the sum of these two? Well, I just pick the coefficients and sum the coefficients. So this will be the sum of y prime I plus y at 0 ddxi. No? And what it means to multiply by 6. Okay, I just do it. I just do it at this level. This solves every problem but creates a new one. Which one? That this structure as a vector space is independent of the chart. Okay, I use the chart to make it into a vector space. But if what does it happen if I pick another chart containing the same point? Do I get the same structure? Do I get isomorphic vector spaces or not? Or, in fact, isomorphic for sure because they are finite dimensional. So, and every finite dimensional vector space is isomorphic to Rn. The real problem is, are they canonically isomorphic?
Yes, because we use the change of the transition there.
Okay, but that's exactly the computation actually we already did. So I'm not going to redo it, to do it again. Because, okay, now instead of u and v, you have x1, xn. Okay, this is something you can handle. Okay. But it's important you realize that there was a problem. Then the problem is easily solved. Do you use the change of variable form? Again, the chain rule will make it appear the Jacobian of the transformation here. Okay? So they are canonically isomorphic via the use of the Jacobian of the change of chart. Okay? Okay. But remember, this is important, so let me write it, even though I said it already 2 or 3 times. TPM, now from now on, the tangent space is, if I have a chart around my point, is the vector space generated by these standard vectors. So, okay, every time this makes sense. So every time I have a chart. And now basically, again, we keep on reviewing what we did for surfaces. That's why we can go quite fast now. Because what would be, once we have a tangent space, we can immediately build the differential of a map. Okay. So, again, in the situation as before, so we have M1N, M2M, and the smooth map in between. Okay. What do I have to do if I want to define d phi? So, of course, I pick P in M1, and I pick V in TP M1. Okay. If V is a tangent vector, it means it's an alpha prime 0 for some alpha. Okay? So this means V is equal alpha prime 0 for some alpha. And then, of course, as we did already for surfaces, put beta to be F composed alpha, phi composed alpha. Okay, so this is what? This now is a curve here by composition. So I can look at beta prime at 0, define, and now this is of course what I like, so I define it immediately as the differential of the map applied to the vector V. So, okay, now the definition tells me where it's coming and where it's going. So d phi p is going from TP M1. This is by definition what? It's the tangent vector to a curve, so it's a tangent vector to phi of p, no? Because beta of 0 is phi of p, to M2. Okay? But exactly as for surfaces, we have 2 problems. Is it well defined? And then it is what we hope. Is it linear? Is it, okay? So 2 remarks. D phi p is well defined, meaning when I pick V, I say, well, I know there exists alpha, but there are many alphas. So that's the problem. I mean, does this care if you take alpha 1 and alpha 2, giving the same alpha prime 0? Does this change? So this means it's well defined. Second, d phi p is linear. Because that's what you want. I mean, the differential has to be, in your mind, the best linear approximation of any map. So if it's not linear, it means it's a wrong definition, even if the definition is well posed. Okay, so how do we solve these 2 problems? By exercise, because it's exactly the same proof. Okay? Meaning what? I just remind you the strategy. You write down these objects in a chart. you do the computation, you find the expression, and you notice that the expression does not depend on alpha. And the expression is actually giving you automatically a linear map. Okay? That's what we did. It's exactly the same proof. Huh? There is nothing. It's just you have a bit more indices. Okay, so but out of this, what we gain is that, of course, I mean, I just forgot to say how we call it, but this is called the differential of phi at P. Okay? Other thing, once we have the definition of a smooth map between manifolds, automatically we can speak about diffeomorphism, which is kind of the equivalence relationship among these objects when we are going to classify them. Of course, I don't even write it, okay? Diffeomorphism will simply mean it's a map which is bijective, smooth, with inverse smooth. Okay? On the other hand, an important property, an important observation is worth doing, because if phi is a diffeomorphism, you automatically get something, diffeomorphism. So phi goes from M1 to M2. So of course, two manifolds to be diffeomorphic, the first thing they need to have in common is the dimension. Okay? And actually, d phi, it's automatic. It's actually, in fact, it's probably the simplest way to prove what I just said. To check that if something is a diffeomorphism, d phi, now this goes from where to where? It goes from TPM1 to T phi P M2. Is a linear isomorphism for any P. Okay, so the differential of a diffeomorphism as always have to be an isomorphism of vector spaces. Okay? Actually, that would be my way to prove what I just said. Why do they have to have the same dimension? Because otherwise, I think it's a bit tricky. I mean, this automatically tells me that the dimension of this is equal to the dimension of this, but these dimensions as vector spaces are exactly the dimensions of the original manifolds. So this automatically proves the claim, because otherwise it could be a bit tricky. Eh? Now I don't remember.
We proved the result in algebraic logic class that would imply, because this map would deduce that if we have Rn and Rm, we have two isomorphic open sets. But in algebraic topology, using homology, we prove that this implies that.
That's what I said. It's a bit tricky.
Yeah.
You need a machinery. I mean, otherwise you need to know to use some kind of sophisticated stuff. I mean, why? Actually, this is a straightforward computation. Okay. So now, in many situations, when we'll be trying to prove that something is a diffeomorphism, is always, of course, very difficult, and there is no general method. But of course, this is a necessary condition, so typically you try to construct maps which at least satisfy this property. So at least the problem is, to which extent is the converse true? Okay, suppose I can construct a map which has this property of being a vector space isomorphism at the level of tangent spaces. Can I actually go back to the level of maps? So let me at least state it, because it's a very important observation, is that actually, well, if if a map between two manifolds, I mean with the same language, if d phi p from Tp M1 to T phi p M2 is an isomorphism, then phi is a local diffeomorphism. Okay, so it's true the converse only at the local level, which is actually the best you can hope, because of course the invertibility of the differential of course can tell you something only around the point P. So for example, it will never be able to tell me that the map is injective. Okay, if I have 2 points very far away, which are actually going to the same point, I mean, this property will never see it. Okay, the best it can tell me, okay, locally it's doing nothing. Okay, but globally I will not be able to say anything. Okay. Okay. And then final part of the story in terms of language. We are building a language now, and actually I'm mostly referring to the corresponding proofs for surfaces. So among maps, of course, if you have a diffeomorphism, you win. But let me give you another pair of words. Because, okay, if you reach the point of having a map which is an isomorphism of vector spaces, you are very happy. But suppose you can reach half. I mean, isomorphism means 2 things, injective and surjective. So maybe sometimes you can reach injectivity, sometimes you can reach surjectivity. So what does it really mean geometrically to reach half of this condition? Okay, so again, definition, let's associate a word to anything, to all this situation. So phi is an immersion if the differential is injective. For any p, note that this gives me automatically a condition on dimensions. Okay, let me go back here. So n was the dimension of M1 and m is the dimension of M2. This can happen for sure only, so this implies that n is less than or equal to m. So you can immerse something small into something big. That's even why the word, okay? Again, if, moreover, so if it's an immersion, and you know something big, but more, something like Fm1 is homeomorphic to M2, sorry, yeah. Well, no. If M1 is homomorphic to F of M1, if moreover M1 is homomorphic to F of M1, then phi is called an embedding. Now this is a bit more delicate, but you need to appreciate what it means. Now, M1 is a differentiable manifold, so it is a topological space with the induced structure of the manifold structure. Okay? Phi of M1 is a subset of M2. Okay? any subset of a M2 is a topological space with the structure induced by the manifold structure of M2. Okay? Any subset of a topological space gets a topology. So now what is written here is that the original topological structure is the same as the one which the image gets from the target. We have seen really in the lecture one example where this does not happen. This was the real line. I think I call it the volume of the cart. No? It's a curve. So this is a curve where, so this is R. Now if we want to exaggerate in difficulty, this is a differentiable manifold with the topology and actually the standard topology, the Euclidean topology. This goes into R2, which is a differentiable manifold. The image gets a topology, which is not the topology of the domain. Remember all this story here. Okay? So this and this are not homeomorphic. So this is not it's an immersion. An immersion means what? The tangent vector is never zero. Between curves, because it's one-dimensional, so being injective, the differential is the same thing as never vanishing. Okay? But this curve has this property. So this is an immersion, which is not an embedding, because these two topological spaces are not the same. Okay? So this is, for example, the prototype problem that you face passing from immersions to embedding. Okay, so this connects also to... Okay, and just to finish with the language, hopefully, if you actually take right away, so if you have an ambient manifold, let me call it M2, and now I actually take a subset, N, I can think of this situation as a map from, because there is the inclusion. I think of the inclusion map from N to M2. Okay? Now, if this is an embedding, with all the structures induced, no, you see, everything induces things on N, on the embed. If it turns out that this is an embedding, then we call N a submanifold of M2. Okay, that's just a special situation of the embedding property. Okay? So that's when a subset is really a submanifold. So you can actually think all the theory of regular surface, now you can phrase it as the theory of two-dimensional submanifolds of R3. Okay. Everything we did was because everything was a two-dimensional submanifold of R3.
I have a question. If we have an embedding, does the image phi of M1 is diffeomorphic to M1 or not?
At that point, yes. Well, it's homeomorphic by definition. Let me think. It's really a question about pathologies, right? Because the answer is morally yes. So now we have to be careful just to say, okay, two things are homeomorphic. The differential of the map, I know it's injective. What else can go wrong?
It is also surjective. Because of the dimension consideration.
It's also surjective, so it's locally, because you see, the only problem is that it's certainly a local difference. You are here in this situation. If you replace M2 by phi of M1, you are in this situation. So it's a local diffeomorphism, and plus it's a global homeomorphism. Is there anything else that can go wrong? No. No. I bet.
because otherwise, giving this the word embedding would be strange, right?
Yeah, no. There should be any more. There shouldn't be any more pathologies possible now. I mean, if the same map is a global homeomorphism and local diffeomorphism, that should be a global diffeomorphism. Yeah, I think it's true. Okay. Yes, actually it is true, because now it's just because it's 1 hour and 20 minutes that I'm here teaching, but of course, what do you need to prove? So it's a global homeomorphism, and you know that it's a local homomorphism around every point, diffeomorphism around every point. So, and then, okay, this, you know, put it on the left. Now, on the right, what do you have to prove? That this is a global diffeomorphism. Meaning what? It's injective, surjective, and you know. Homeomorphism, you know. It's smooth, you know, globally. And the inverse is smooth. But all these are local properties, and you have this proposition here. So, okay. Now, okay, we won't enter the theory of some manifolds. Okay, I'm just telling you because, of course, it's a very popular and big part of the thing, but of the story. But I don't really want to enter this. In some sense, you can rephrase this proposition at the non-linear level. So this is the linear level of something you can actually rephrase using these words. So, for example, let me just say it in words. If you take an immersion between M1 and M2, then actually because of this, essentially, or actually this is another rephrasing of the inverse function theorem, or the implicit function theorem, if you want. So, because of this property, you can actually prove that any immersion is locally an embedding. If I restrict phi, if I know it's an immersion, and I restrict it to a sufficiently small neighborhood of a point, it becomes an embedding. You see, for example, this is what, think of this situation. Here the failure of being an embedding is clearly a global failure, because around, if I'm around this point here, I can pick a sufficiently small neighborhood where this is actually an interval of R, okay? And even here, if I pick a sufficiently small interval, I won't see this other bit. If I take the restriction of the volume of Cartesian only around any point here and a small interval around it, of course, everything else disappears, and I'm left just with a beautiful piece of interval also here, okay? So if you think that this is the kind of pathologies you have to avoid, you realize that actually why this statement I said is true, okay? But any immersion is a local embedding, okay? Do you agree? You can see the proof. You can see a proof there. So, okay, let me move on. Well, actually a nice way to end. Yeah, let's do two examples if we manage in 10, 15 minutes. So, I completely skipped as a kind of example the case of the sphere, which remember it should be always example 1. And now let me go back. Let me go back to the sphere. Now the sphere in any dimension, and now as usual I take the sphere with center of the origin and radius 1, so Sn contained in Rn plus 1 for me is just okay, center the origin of radius 1, nothing will change if you change the center and change the... Now, of course the picture you draw is the two-dimensional picture, but now we are in any dimension. And actually I've given you directly as a homework to compute the stereographic projection from one point. Have you already done it? So you did it in dimension 2. Okay. The computation is actually the same in any dimension. So okay, I can use this computation. So if I pick n is of course the point 0, 0, 1. So the stereographic projection, let me call it pi, or pi n actually should be a bit more. Let me call it pi n. So the projection from the North Pole, from this point here, is actually a map from Sn minus the North Pole to Rn. And actually I can use already the expression. So this takes x1, xn plus 1. Of course, the only restriction is that xn plus 1 is different from 1, because it's not to the North Pole. And this goes to x1 divided by 1 minus xn plus 1, xn divided by 1 minus xn plus 1. Okay, this is the output of the exercise in one way. Then of course, if you want to prove by using this type of maps that the sphere is a differentiable manifold, of course this would be enough to cover everything except one point, so then you need at least another one. So for example, you can construct, that's why I put the index here, you can construct the stereographic projection from the South Pole, for example, actually from any other point at this point. And you construct a chart which covers also the North Pole, and this will have the same, I mean, the dual expression, okay? So that, for example, from the South Pole it will be minus 1 here, so the expression would be actually plus the same, okay? Okay, so this is a nice way to prove, because at this point, once you have these two expressions, you have to write down the change of charts. Okay, so now the change of charts will be, okay, I don't even write, it's clearly a smooth function and so on. I mean, what I'm really going to, okay, so this is the simplest and most elegant and most geometrical thing. At the same time, remember, you could cover the sphere by, so in dimension 2, how many? 6? Half spheres, no? Remember, essentially the implicit function proof of the fact that the sphere was a surface. Okay, so for example, I can take the piece x n plus 1 positive, no? The upper half sphere, and then I can write this part as a graph over this disk, no? So that becomes, I take the equation, and then xn plus 1 becomes the sum 1 minus the sum of xi squared, but now I goes from 1 to n to the power 1/2. And then I have the lower part, and this of course, this is restricted to the disk, no? Where this is positive. Then I take the lower part and so on. Now of course in dimension n you get what?
2 plus.
Well, every coordinate gives me 2, so it's 2 times n plus 1 charts. No? And then, of course, actually here again, you should prove that, for example, when you take this chart here and this other chart here, the intersection over this quadrant, the transitions are smooth and so on, but everything it's really simple. So these are two different ways. Of course, once you have this, you should prove, actually now you know that there is a little problem to face, that this, so in some sense you could speak about the stereographic projection structure and call it the graph structure. Are they the same? Are they diffeomorphic manifolds? Okay. Of course, the answer has to be yes. And in fact, you even know which is the diffeomorphism. The diffeomorphism has to be the identity. So what, but it's a good mental exercise. What should you prove? To prove that Sn with Sn, with the charts pi n, pi s, for example. So this is one differentiable manifold. And then you have Sn, let me say gamma f, just to remember, this is the graph structure, okay, with these 2n half spheres. Okay, so what do you have to prove in order, and then I claim that the identity here is a diffeomorphism.
That composing one with the inverse of the other is
Exactly, you need to prove that the coordinate chart as a graph is a smooth function in the stereographic projection charts, and vice versa. Okay, so you need to prove that the identity, of course, the identity is injective and so on. You need to prove that it's smooth and the inverse is smooth. Smooth means write it in charts and check. Okay, so this would be a bit boring, to be honest, but it's a good, healthy exercise. Okay. Very good. Now we have these two structures, we prove they are the same. And now the point I was hoping to make was to go back to the projective space. So because actually the sphere, so remember I started the lecture by saying, by describing the projective space and then say, well, it looks like a cousin of the sphere. So let's be a bit more precise. In which is the real relationship between the sphere and the projective space? Is the following. The sphere covers the real projective space. In which sense? You say it's a quotient. The real projective space, I really want to say it's a quotient via a map pi. Okay? So I take 2 points, so you see every point of the sphere, of course, is a point of Rn plus 1 minus the origin. Okay? So I can really say, in fact, pi of p, if I take a point p here, pi of p, I just look at the equivalence class of p. Now, what is, this I could have said it from Rn plus 1 minus the origin. Now, what is the difference saying it from Sn? From Sn, the point is that, of course, I know how many elements are equivalent in Sn. I know exactly, I can count them. Before, in R plus 1, it's a whole line. Here, how many points are equivalent? Are mapped. Equivalent now means they are mapped onto the same point. And now there are just 2, because if this was the line, of course, there are only 2. Well, of course. Okay. It's the first appearance of Bezout's theorem. Anyway, you check. It's a quadratic equation, intersect a linear equation. So, in this case, of course, you do the computation by hand, but it's nice to think of the general theory behind. Okay? So there are only 2 points, which are, in fact, I can even write them down. It's p and minus p. Okay? P and minus p are the only equivalent points. So of course minus p is always called the antipodal point on Sn. Okay. And now you see, the graph structure of the sphere actually is more suitable to think of this situation than the stereographic projection structure. Because you see what is the property of the graph structure. For example, if I take here, I would have had two, so the xn plus 1 positive, xn plus 1 negative, okay? They are actually, each of them contains one and only one representative of every equivalence class. Do you agree? I mean, there is not, while in the case of the stereographic projection, one chart, in fact, contains everything minus 1 point, so there will be always antipodal points. Okay, the graph structure separates the two possible equivalent points. So in some sense, I can even use the graph structure and quotient it. Okay, I can really take, I can construct yi, so let me call the graph structure xi plus and xi minus, the charts with obvious notation. So one is the chart taking the ith coordinate positive and the ith coordinate negative and so on. Okay, so this is the notation. So I can construct yi from, well, ui, I will tell you, but just in words, otherwise it takes 3 minutes, xi plus, oh, sorry, this is not in PN, in PNR or RPN. I think I started by denoting in this way. Yi is equal to pi composed xi plus, okay? Where ui is the domain of xi. Let me not write it because of course it's a disk, but it's a disk depending on I in the other plane. So for n plus 1 is the horizontal disk. It's the domain of the graph function. Okay, but depending on the coordinate, this will change. So I don't want to write an expression. Okay. Now the point is that this is 1 to 1. Okay. Because this one was 1 to 1. And moreover, if I take the change of is smooth, and actually it's automatic. This is, again, now it's very convenient because I don't even have to write it down essentially, because this would end up being the change of charts on the sphere in the appropriate charts. So what I'm saying is I take the charts of the sphere and then I project it. But actually I'm taking sets which contain one and only one equivalence class, point in every equivalence class. So projecting is very simple. It means not touch. Pi, restricted to this set, is doing nothing. Okay, so everything becomes okay, so this gives me another manifold structure to this thing. And in fact, if you think, you can think of this operation of like taking really the quotient with a group, even the original one. When you say P and R is actually the quotient of Rn plus 1 minus the origin quotient by R star, no, by the equivalence relation. In fact, I've already written as a kind of an action of something. But here in this situation, the compact situation, it's much, much clearer what's going on, because I'm really saying that this is Sn, and now which is modulo the equivalence relation given by the antipodal points. But actually, if I want to replace this by something algebraic, what can I say? It's the action of Z2. It's plus minus acting on a point. So plus 1, of course, gives me P, and minus 1 gives me minus P for every point. Okay, so 2 observations and we are done. This is, in principle, another manifold structure on Pn. So now So you should go back to the first 5 minutes of the lecture and say, okay, but is this the same as the one I described at the beginning? Yes. Which is a diffeomorphism? The identity. What does it mean? Write down, for example, these charts in the coordinates I described at the beginning and check that they are smooth and vice versa. Okay? Second observation, we had an action of a group on a manifold, and in some sense, you see that everything was adapted to the action of the group. So in this situation, I can really build everything by hand. So there was a system of charts of the manifold, constructed in a way that every chart contained one and only one point of the orbit of the group. If there is P, there is no minus P. In this situation, it was very clear. Okay, upper or lower, positive or negative. Okay, and in this way, once if I can construct charts of the manifold, which is so nicely adapted to the action of the group, I naturally have a manifold structure on the quotient. This is just what I want you to realize. Because this is, in fact, a completely general phenomenon. It's a very important phenomenon, okay, that we will analyze a little bit better. Okay? So group acting on spaces is actually one of the most interesting ways to produce interesting spaces. Even when the ambient space is boring, Rn, Sn, there are interesting group actions that creates interesting spaces. Okay, so it's nice, it's important to understand how to give a nice structure to the quotient. And this is the prototype situation. Of course, you cannot hope anything better than this. Okay? I mean, charts that are not interfering with the group structure and so on. Okay? We will see how this develops, okay? Unfortunately, I know students hate this. Everybody, I mean, since everybody has been a student, everybody has hated it, this kind of things, starting from the topology. You know? The quotient topology is always the worst part of topology for every student. The quotient structure manifold is really the worst part, but actually then when you start working, you realize that these objects appear continuously, and they are very interesting. So try to make an effort, okay? It doesn't matter if I say it, I mean, everybody will keep on disliking it, but it's, it's still important anyway, okay?